Thank you for the introduction, Bob. Hello, everyone. Hello, everyone. So my talk will be on mostly achieving high performance for running code, and I will focus on parallel processing. So there are a few ways you can make your code in general run faster when you have a program. The first one is the simplest: get better equipment, better hardware, more powerful CPU, more recent, some specialized tools. There are CPUs with some specialized instruction sets for certain tasks. You can get GPUs traditionally for image processing. You can get some specialized software that works a bit on everywhere. For example, ADMB and TMB are two examples for optimization. There are some libraries that make also computing run faster that are a bit more general than in R. The BLAS and LAPACK libraries, I think, are also defined in C++. You can do some approximations, and you can also do some parallelization, which I will focus on. It should be noted that there are some rare languages where parallelization is already embedded in the code, where the user does not have to do any work to make parallelization happen. The compiler already does it in the background. Haskell is an example of a language that does this automatically. It is limited, but the user does not have to do anything to make it work. So I will focus on parallel processing in this talk. There is some terminology that I will use, so I need to define it first. So a processor and a CPU are synonymous terms. There are some people find some differences. Sometimes a processor is synonymous to a core instead of a CPU, but the difference is really small. A CPU is a central processing unit. It is composed of multiple cores, and it is an electrical circuit. So it performs operations such as adding bitwise comparisons between two bits, for example, AND operations, or operation exclusive or if statements. It performs every very simple task. It is done directly in the electrical circuit. A CPU is traditionally composed of multiple cores. It is a trend that has been growing in the last 10-20 years because cores they have become cheaper and more powerful. So now we can just cram a bunch of them into one CPU. A cluster is a collection, typically of machines, but it can mean also a collection of cores. On the software side, at the lowest level, the code runs in threads. So there are just basic sequence of instructions. Typically, ideally, they would run one per process. So here a process will be just a running instance of R. So you can have multiple, but by default, there's only one when you run R or RStudio. And when you want to have multiple instances of R running in parallel to split your tasks between the two of them, there are two main ways to do it. The first one is called a socket. So each process has a dedicated memory space where you can define variables that the process will use. So a socket works everywhere. That's the main advantage. It duplicates the entire process and the entire memory space. Now, with certain restrictions, you can use a fork instead. Currently, forks are only available on what are called Unix-like distributions, so macOS and Linux distributions such as Ubuntu, Fedora, etc. The main difference with the socket is that the memory space is not completely duplicated. It is the same until some change happens. So if you have 100 cores running, you would have one use of the memory space unless some change happens. This is a big advantage on Linux and macOS because the memory requirement is much smaller. There is also some language that has been used traditionally, the terminology to specify the parent process and the child process has been master-slave, but in computer science in the last few years or decade, those words have been changed due to some racist connotation. So now it is not as standardized, but usually you would see those words be redefined as main and worker process, parent and child, chief, worker. But it used to be master and slave. So as I said, the socket, the main benefit is that it works everywhere, including on a collection of computers, a cluster. There are no restrictions really, but it is a bit slower because of all the memory management and uses a bit more resources. Forking is more efficient, less memory required, a bit faster because there is no overhead to manage everything, but it only works on one machine and on Linux distribution or macOS. So this is just some terminology that I will use a bit later. So a brief history of the main packages. I insist on main because there are many more, but the most popular ones historically have been the Snow package, the simple network of workstation. This uses the socket, so it works everywhere. But then people thought, I use a Linux computer, I can do it. It can be done better with forking. So multi-core package came to make use of that of that requirement. If you want to run some specialized loops, some advanced for loops, there are two packages that can be used with those. It's basically do and then the name of the package. Do Snow, do MC for multicore. After these two packages came, there are some people who wanted to try and standardize the whole thing instead of having to use one package every time. So Parallel is a wrapper that combines the benefits of both and streamlines the whole process. You wouldn't have to use one package for one computer and another package for another one. And then the Future package is a bit more recent and is a bit more standardized because the main concepts of the Future package are available in other programming languages such as C++ and Python. So if you understand how that package works on one programming language, the concept is very similar on other programming languages. You can look at more details on the history on high performance computing in the cranrproject.org. Now, there are multiple situations where you would want to parallelize. For example, in brute force search in cryptography or in statistics, it would be, for example, in machine learning, such as cross-validation techniques, random forests, genetic optimization, Monte Carlo simulations. There's a small cost to parallelizing because you have to write the code, but it can be very efficient. When every task is independent, for some reason the problem is called embarrassingly parallel problem. Sometimes you can see it named perfectly parallel problem or delightfully or pleasingly parallel problem. If it's not embarrassingly parallel, it is a bit more difficult because each process would need some way to communicate with the others. I will give a small example later of this. Now, when do you want to do the work to parallelize? You want to do that work when you have some substantial gain from parallelizing. So the classical way to estimate the acceleration when you want to do some parallel processing is with something called Amdahl's law. I'm not really sure why it was defined as the inverse ratio of the task speed, but that's how it is. The idea is you have some workload, some fixed workload, so it is simplified in the formula. It does not appear. So T would be the time with a single core, and it can be split into a part into a sequential part that cannot be parallelized and the part that can be parallelized. And if you have n cores, the idea is the sequential part is fixed, and the parallel part, the time can be divided by the number of cores, because you will split that work into n cores. So if you simplify this, the formula becomes this one. So as an example, if half of a problem can be sped up by a factor of 10, the speed up from this can be up to 1.82. Now, historically, this law works well, but the problem is that the workload has a fixed size. Some people have seen empirically when they were doing the work of distributing their workload on multiple computers that the more cores they have, the more they will increase the amount of work that can be parallelized. So this can be adjusted by with this law, and the main difference is that the workload, when it is parallelized, is multiplied by a factor of n. Gustafsson has realized that empirically, when he had access to n cores, he multiplied the parallel workload by the same amount. So the end formula changes slightly, but the idea is really that the workload gets multiplied by a factor of n. So in this case, the parallel workload would be multiplied by 10 in this example, and therefore the speed up is much more massive. In practice, unless you run a large project, or you would use the first law because it is quite simple and a decent estimate. There's a way to generalize this, because some people found out that, well, why multiply it by n, the workload, instead of multiply it by any function of n. So this is called Sunni's law, and also called the memory bound speed up. It is a bit simplified because originally the factor is not a function of the number of cores, but of the memory available, which is itself a function of the number of cores. Because if you have 10 computers, then you have 10 times the memory, but it can be, you can run into memory issues. So the general law is slightly more complex, but not by much. And the idea is really that you can multiply it by any number you want, the workload. There is one concept to keep in mind if you do some parallel processing. It's that so the number of processors on the bottom is arbitrary, but the trend is really the important thing. If you increase the number of processors, after a certain point, you'll start to see negative returns, because the overhead of communicating between all the processors, all the different computers, will increase, and after some point, it will become more than what you would gain from adding processors. So if you have access to a large amount of computers or cores, just be aware that this can be a problem. Now, I will go into some embarrassingly parallel problem because they are the easiest to handle. So this is when every task that you want to distribute over multiple cores or over multiple computers is completely independent. They do not need to talk to each other. They just run and return some result. One way to do this for statistics people is using the divide and recombine method published by Guha et al. In 2012. The idea is if you have a program that an optimization function that takes too much time to estimate on a massive data set, you can run it in parallel on subsets of that data set and then recombine each of those estimates to give one end result. The statistics behind this are available in that paper if you are interested, but this is one example of how you can apply parallel processing to statistics. Now, if you have a non-embarrassingly parallel problem, the de facto standard for this is a method called MapReduce. This is a simplified version of the MapReduce example, but the main concept is there. The classical example is, let's say you want to count the frequency of the words in, let's say, all the laws in your country. That is a massive amount of text that you want to analyze, and the word count from one document is dependent on the word count of another document because you want to have everything aggregated. So ideally, you need some way to distribute it to multiple computers and make it work somehow. So the MapReduce is the standard for this. The way it works is you have some input data. So here it's just a few words, a few random words. You split that random that data into different mappers, which will read word per word and send each word with an identifier for that word to reducers and give them the value 1, because here each word is encountered once when it is taken from the text. Then each of those counts is sent to reducers, which aggregate all the inputs that they take and just run a simple sum here. Then from each of those you can get, so the first one would maybe say that Blu-ray appears twice in what it has seen, CD appears 5 times, and then there should be a step missing here to reduce everything again because reducers would have some overlap. So this was done by 2 Google researchers in 2008, and this can be applied to a wide range of problems, but this is very simplified, and the values here, 1, are not really useful, but this is an example of how it works when you want to count all the words in thousands of documents. Now, the theory is finished, so let's move on to the more practical part. If you want to do some parallel processing using RStudio, the simplest way you can do it is by defining some R code into R files. And in RStudio, you can just simply go to source and then source as background jobs. RStudio will make it run in a new R instance, and you can do that over over any numbers of R files, even the same one multiple times if you want. This is really the simplest way you can parallelize in R using RStudio. Just click on source as background job, and there is no overhead for you, apart from clicking. If you want to automate this a little, you can use the future package. Previously, you had to, the Snow and Multicore package and others had created new processes, and then you had to worry about copying all the memory blocks. Copying all the memory, for example, if you had defined a variable alpha, you had to copy it to each new process. If you loaded packages and libraries, you had to export all of them and then run some dedicated functions such as parlapply for the Snow package or mclapply, which have different ways of working. This was kind of a mess, and the future package standardizes all of this, so it's the same code that can run on any computer afterwards and any operating system. So, for example, so on top you can see a very basic sum of all the numbers between 1 and 100 done without any parallel processing. You can split that sum into 2 parts to run both of them in parallel. First you have to load the future package, and then plan multi-session. This uses all the cores available in your computer to run sockets, and that's pretty much it. There are 2 methods afterwards to run futures. The main idea, remember, is that you define some code that will be run at a later time, and then how it is run, you can define it in terms of parallel processing. So here we define that it will use all the cores available on my laptop to run in parallel whatever it can. Here I define the first the sum of the first 50 terms, then the sum of the 51 to 100, and then retrieve the values for each of those. You can run it like this without curly brackets, but to avoid any problems, just try to remember to use curly brackets. Then you retrieve the results, and you can get the sum like that. If you don't want to have to bother writing future and value, you can simply use this operator. This is just the same one as this, but with some percentage signs around. Then curly brackets would be ideal, but it works sometimes without. And then you can just retrieve the values. And these two futures will have been run in parallel. Yes?
Can I ask about the method one? Clearly, both those future things has to be executed before you can get to the final answer. So where
yes.
will to get the final answer AA?
Yes.
Then both those processes must have been executed.
Yes.
Yeah. And where will it wait? Let's say FB takes a very long time. Where will it stop?
Value is a function that stops until you get the result.
Right.
There is another way, but to not have to wait until you get the result and actually run it in parallel. But what I'm trying to focus on is this, because this is done automatically, and you don't have to bother about all of this. This will wait until the future FP is resolved.
Yeah.
And it will start to be resolved at that time.
So it will start when it sees the value. It doesn't start when you say future.
As far as I know, no. It starts here and waits until this is resolved, then waits until this one is resolved. So this is not really interesting, but this is one way of making that work. This is just faster to write, and you don't have to bother about writing future parentheses and value parentheses or resolve. There is a function called resolved where you can just ask if the value has been computed. It will compute it, and you can do other stuff in the meantime. But the main idea is really go through this. It's simpler, that you don't have to bother about all the rest. If you are the type of person who likes to use apply functions and map functions, you can do that with a package called future.apply, and all the traditional functions that you use, apply, lapply, sapply, vapply, etc., are defined with future underscore the name of that function. So, for example, if I compute all the sum of all words between 1 and 5 with future lapply and just lapply, the result is identical. The results are identical. If you like, future replicate, sapply, apply, vapply, most apply functions can be futurized with this future underscore the keyword. If you are a user of the per package, which goes into apply functions a bit more deeply with map functions, you can just, it is the same approach with future map to future modify, and the for package instead of per package. So if you were to do nested loops, so a loop within a loop, and you want to parallelize that whole thing, by default it is a bit tedious, because so here we load the packages, list env, because we need to store environments in specialized lists. By default it doesn't work. And the way to make this work is to plan the parallel processing backend with plan and then a list of all the ways you want to do this. So here there is a multi-session, so it will use all the cores on my computer and as sockets, and the inner loop will be done sequentially. I could rerun multi-session or multi-core or anything I want, cluster distributed, but So the idea is here I have a for loop and I run some future here, and inside that loop I run another future inside a loop. This is a bit tedious, but it works out okay. So the result is here the identifier of that process, the number of that identifies that process. So in the inner loop I ask to be done sequentially, and the outer loop in parallel. So I between 1 and 3 will be run concurrently. The result is that the outer loop uses the same process number. Then the second outer loop uses the same process number 3 times sequentially, and then the same process number again 3 times, but a different one. So it works, but it is a bit tedious because this is not very intuitive. So a way to make this more pleasant is to use a tool called the for each loops. By default, they can work with or without any parallel processing. The idea is that the for loop will be a function that will return the result, and you can define how those results will be combined. So the way to do this is I specify dot combine. So here it's C for simply concatenating all the results in one vector. I specify the loop iterator, and then do and return the process identifier. So here there is no parallel processing, and I get one process has been used for that loop. If I want to parallelize this, I load the doFuture library. I have to call this because yeah, I have to. And then I ask to plan a multi-session, so use sockets, and I want to use only two processors, only 2 cores out of the ones that I have. And then if I, instead of do, I replaced with dopar, then 2 processes have been used. So this example is trivial, but the idea is to show how a minimal example works. So the idea is load the doFuture register, plan how you want to do the parallel processing, and then dopar, and it works. Typically, you would be able to run even large amounts of code here, because this is basically a function. So you can run a lot of stuff. You can do anything you want inside, and then as long as you return some result, it will combine all of them with some function. You could use list to combine all your elements in list, or rbind to combine them in a table, or columns with cbind. So then the next topic is nested loops. So as before, if you want to parallelize a loop within a loop, if you want to parallelize outer loop and inner loop, with that framework, you have 2 ways to do it. The first one is here I define 3 cores to be used in the outer loop and 2 cores in the inner loop. I can just repeat dopar and dopar. The first one returns 0 in the vector 5 times. The second one returns 0 in the vector 5 times. This is really trivial, but it is short and to the point. The second way to do it is with only 1 loop, because the idea is to use this strange operator, which will say everything inside will be done sequentially, will be done in one process, will be done, the task will be, all the tasks inside will be streamlined. There is no inner loop, that it is just a concept. So here, the first loop will run 1 to 5. Everything inside this will be one sequence of tasks that will be run with 2 workers. And I can define inner loops again inside, and inner loops to infinity. This has some advantages sometimes. It depends on the situation, but just remember that it is doable with that operator. One also important part is if you have a few millions of tasks, let's say, a few millions of very small tasks. Each time the loop goes to the next iteration, it will run a new future, and you run into all the overhead that are done with futures. If you have to run a small tasks a lot of times the overhead can become quite massive. So what you can do is combine a lot of those tasks and just say, do not create all the overhead that is required with a complete new iteration, but combine them somehow. So here, if I try to combine it with a size of 3, an average number of 3, the first 3 are combined into the same process, which will run the first three tasks at once. Then the second process runs 2, and the third process runs 5. It tries to do an average somehow. There is a heuristic behind it. So this can be useful mainly if you have a very large amount of small tasks, because otherwise you will run into a lot of overhead. So the way to do this is options future and then the chunk size, which will be the average number of tasks that each process will run on your loop. Now, one of the most important things, especially to statistics, is randomness. If you simply set the seed beforehand, run a parallel loop on multiple processes, you will have some results. But if you try to run it again with set seed, so here I generate a random number from the standard normal distribution, and then I try to set the seed without parallel processing to debug or to retrieve the similar results. The number is different because the seed doesn't work like that. So one way to solve this is with a neat package called doRNG, and after you load that package, notice the dopar becomes doRNG. Then you do not even have to set a seed because the results will contain all the necessary information you need to set the randomness. So here I do the same thing as before, and if I look at the second result, I have minus 0.15. If I set the random seed using this, which is just the RNG attribute of the results objects that I got, and return the same random number, I get the same. So this is a way to set the randomness to reproduce results later. You do not have to do this if you don't have to, but it is nice that you just remember that if you use doRNG, you can retrieve the randomness seed and reset it and make it work later. Now, let's say you have some parallel program that you want to run, and it will take, let's say, a week to run. You don't want after 2 hours to it has a bug, and you don't notice until the end of the week because you have no way of checking that it has run. One way to do this is to check that it is if it is progressing nicely is by monitoring the results. One way to do this is by emailing yourself every, 10% of your loop, or every iteration of your loop, or every 1,000 iterations. For now, the mail server at uib.no is still working. So if you want to use Gmail, you can, but it is slightly more complicated, so I will not get into it. So in R, this works on every programming language. This is just an R example. So the way you can do this in R would be to use your ID. Your first and last name does not work for some reason. Then you define a message. You send it. Here I send it from myself to myself with some subject, and then specify the host name, smtp.uib.no, my username, and my password. Then I get an email. So you can use that code inside the loop. For example, every 10% of every 10% that the program does, or some way you have some way of monitoring. If you don't want to use emails, another way is to use a public website called ntfy.sh and then some letters afterwards. If you go to that website and all the messages that you send through this command will appear there, and there is an app for phones, and you can do it on the browser directly. So those are the two main ways that I personally have used to check if something was happening, if the code was broken. If I didn't get any notification for 2 days, then I knew that I needed to check. This is useful for long-running code, not for 1 hour, but the main thing is you can send yourself emails with Rebus system for now. Now, if you have a smaller amount of code and you want to check that you have not run into an infinite loop, you can monitor through a progress bar. I will show a video a bit later. So just use the progress R package, and then you can define a progressor inside your parallel code and increment it with P. There are 2 main ways to do it. The simplest is to define the global handler true, and then you can use that function directly, or without defining it, you can use with progress. If you need to remember how to do it, just look at the progress R package, and there is a nice explanation of how to use it there. But the interesting part is it can be used for parallel processing. So if the video works. So I just copy-pasted the code from before, which just waits 2 seconds, iterates the progress bar, and then goes to the next loop. So this is done in parallel with 2 cores in the background. You can do it with any number of cores, any number of computers, and it just works. So this is a slightly different way of monitoring that everything is running correctly and the code has not crashed 5 hours ago and you didn't notice. If you need to do some non-embarrassingly parallel problem, you might want to record results in a file, for example. If you have a cluster of computers, you might have a storage somewhere on the network, and you want to record some results in that file. The main problem is those processes do not innately talk to each other. So they can sometimes just all write at exactly the same time on the same file, and that will cause problems. I have mostly noticed that those problems increase the more you write on that file. So here I write 1,000 times with 1,000 cores on 1,000 processors on my laptop, 11 processors on my laptop. I write 1,000 times each word with then a return line, a return carriage, then the second word, then return carriage, then third word, return carriage, and do nothing else. Then I look at the last 50 lines and the words are combined and it is not done as I would have wanted. So this would usually happen on non-embarrassingly parallel problems because you need some way to retrieve the results onto a file somewhere. Some results that you cannot retrieve otherwise. So the way to solve this is Flock package. Do not confuse it with FileLock. There are some problems with it. The idea is that you define an access condition to the file that you want to write on. So here, this creates a file called a lock file. This creates a lock on a file called lock file, and then does any task that you want, and then unlocks it. So when other processes try to lock it, if it's already locked, they have to wait until it's unlocked. So the idea is just an access condition on the file, and each processor can say, I have the only exclusive access to that file for some amount of time. And then each word is printed correctly and there are no issues. This is a problem that you might run into, but not necessarily. And now, if you want to go further into parallel processing, some notable examples of what can be done is through the first mainstream project, which was called the SETI at-home project. The software that it runs on, that you can run it on, is called Boink, for some reason. This was done because apparently astrophysicists require a massive amount of computing power, And so one way to do this for them is to distribute it to the general public, and they can run that software at home. It will use parts of their computer and send the results back to the SETI project to search for extraterrestrial life. Another popular one that was done was the folding at home, where it's the same idea, but the program that you run on your computer does some protein folding. This is and it handles natively all the workload that is generated by random computers online and brings it back, and they have some way to combine it. This is more advanced, but this is one way that that parallel processing at scale can be done. Another way is through a video game. The Foldit video game was a puzzle video game about protein folding. It was popular, I think, in around 2010, something like that. There were a few articles about it, and players just tried to solve some protein folding problems and submitted the results, and it was actually helpful for them. This is a slightly different way to do some parallel processing at scale. If you want to use something like MapReduce, the Apache Foundation has software that is currently one of the two main standards for this. It implements MapReduce, so it's a completely dedicated software to make MapReduce work. It is called Hadoop. There are some R functions to make Hadoop work with R, and it is more advanced. So if you have a small scale project, just use the Future package on R or on a different programming language, it will work. But if you want to do it in a more advanced way with MapReduce, you can use Hadoop. Spark is another implementation of Hadoop, with some upsides and some downsides. It is slightly more efficient and more recent, so it is a bit faster, but it has some troubles with massive datasets, with larger datasets than Hadoop can handle. Now, if you have, let's say, a large project where you have a few hundreds of computers distributed on the cloud, for example, or somewhere, and you might need to handle, for example, if one computer fails, does my entire project crash? Or if you want to be able to add computers to your cluster, you might need some very dedicated and specialized tools for this. So you would need, for example, a scheduler. Here is one example is Slurm. You would need some way to pass messages through the MPI, which MPI is the standard for this, and has a package with R. You also need to manage all the memory that goes in and out of your cluster of computers. One example of this being done was in 2005 by Vincente and Rodriguez, where they had a project that ran on multiple months and dynamic number of computers. So sometimes they failed and they were replaced by other ones. This would not work by default on R. You will need some really highly specialized tools for this. But for your needs on a small scale project, just use R in Futures and that will be fine. So these are the references that I have used if you're interested. I would like to thank my supervisors and my friends for helping me with parts of this presentation. Thank you.
Yes, some questions, comments?
How can you assign or estimate P?
What do you mean?
The efficiency of your, how much you can parse?
Do you mean the acceleration?
Yes.
P is the part of your task that can benefit from being parallelized. So this will be very different on different problems.
So suppose that you have the very good situation, like the car simulation or something, where
If you want to do a Monte Carlo simulation, I guess the entire thing could be parallelized, so P would be 1.
Okay. So there must be a little bit administration at least.
Yes. But if you want to keep it simple, just use Amdahl's law and try to find an approximate value of P. The number, of course, should be obvious, but yeah, P is not always very easy to estimate. But on a purely parallelizable problem, it would be just 1, and the formula would become a lot simpler. Yeah?
How would you go about choosing the number of workers to assign to
Well,
the routine?
typically, you have some constraints such as money that is involved. If you want to use a large number of cores, you will run into money problems. Let's say you go on AWS, which is Amazon Web Services, and you want to rent 1,000 computers. It will cost a lot of money. Even if you run them for 20 minutes, you will run into money problems quite quickly. So typically you would use everything you have available. It's just on a large project, remember that there is a negative return after some point. Also, it would depend on how many tasks you can parallelize. If your loop has 3 iterations, you cannot use, it would be pointless to use more than 3 cores. So those would be your 2 main constraints. And then as much as you can.
And for only one workstation is limited to the amount of cores you have.
Yes. I think it would be fine if you run more than more instances of R than cores that you have available, but then it's not ideal because there is overhead. Ideally, you have one instance of R per core. One thing to note is use always the number of cores you have at least -1. If you use everything, then there will be no processing power left for moving your mouse or updating the screen. It would be frozen and nothing would happen anymore. I mean, the code would run, but you could not do anything with the computer. So just remember to at least leave one processor for the current tasks.
So often a memory usage-based process. So
Yes,
we tend to run into memory always.
the memory is also a big constraint. You do not have unlimited RAM, so remember that. But if memory is a problem, you could use forks, which would not duplicate all the memory immediately, and at least that would be less of a constraint. But yeah.
So a model laptop may have 8 cores, but what about memory? Should you?
It depends on what you want to run in your program. If you want to retain large objects, if you have quite large data that you want to put into memory, that will be a constraint you have to plan for, or just notice that you have a memory problem.
So 16 gigabyte is not enough, or?
It depends what you want to work with. Personally, 16 has not been enough, and I needed to just realize that there were some massive objects I could just get rid of because it was too much. It depends on your problem completely. Yeah?
So, I mean, at the department, math department now, we
Yeah.
have, what type of machinery is available now? We have one server at least, right?
Are you talking about Miloka?
Yeah?
If I remember, it is one workstation with 4 CPUs and 32 physical cores and 64 virtual cores. Virtual cores are a technology where each core is split into 2 virtual cores. So it has 32, and in effect you can use 64 and something like 400 gigabytes of RAM, something like that. It would be a bit difficult to run into memory problems or
Yeah, so I've been using that sometimes, and you are using it
yes.
quite a lot, I guess. But not, so I mean, it's just sort of more of a comment that say, because I have master students now with, you know, a data set of 9 million
Yep.
rows, and of course handling that and building up a statistical model on these things, that's, you run fast into memory issues on a stationary laptop, right? Because
Yes.
that's difficult to handle. So it's more like a comment that, you know, are we ready to, at our department, is there enough sort of computing power available for students who want to do interesting things, right? I mean, or do we need to buy cloud computing for you know, projects that, well, I mean, I don't know, what's your thought about that? I mean,
Well, would you be the only department that
Well,
would
I-
give massive projects? I mean, massive number of data like this?
I mean,
Because
on a national
if-
level, I guess we have
No,
we
but
have a lot
at-
of supercomputers.
No,
right?
but
So
I mean
that's
that
a bit of a hassle to log into and get access to, you know, because then you're competing with weather forecasts
I mean-
and stuff like that.
You can apply for computing fund.
Yeah.
You don't have to pay necessarily
Right.
the national structure.
For students, I meant more at the university level. Are there so many that would do this, or is it really the statistics people? Because if it's just one department, then it should be fine to let them run on local.
Yeah,
But
yeah.
if it's a university policy, then you would have hundreds of students at the same time running massive amounts of
I
code.
guess, I mean, we will see.
It would depend on your needs.
We will see more and more larger data sets, right? So, so it should be something between almost your laptop and like the national supercomputers, right? In order to do stuff on that. So we need to think a little bit about that.
And at least the interesting part is of the future package is that if it runs on their computer, it will also run on local or stationary computers here,
So you can test it out on your own small subsets.
and then just copy paste the code and it will run.
Just a brief as well. Thank you for the interesting presentation. So will this presentation be made available?
Yes, I'm still trying to figure out how exactly. Maybe on my GitHub page or something. But yes, I have video recorded it, so I think the best thing will be to put it on YouTube and GitHub, and that will be the simplest.